Welcome to Astronomy, Chapter 18. This chapter is on cosmology and is going to be a example of a chapter that is going to try to take a really big, broad spectrum view of the universe as a whole. In fact, that's really what cosmology is the study of the universe as a whole. Now, for the scope of this as an introductory class into astronomy, we're going to just barely hop, skip, and jump through Chapter 18. We're only going to focus on a couple of the basic points, the basic tenets of understanding cosmology on the grandest scale. Now, this chapter is, like I said, is a very intriguing topic and really causes you to have to stretch your mind a little bit to think about the universe on the big scale. Remember, this is everything we possibly could know about. And if you go all the way back, I keep referring to my analogy from the first chapter. If you were sitting in your living room and you wanted to know everything about the scope and structure of the entire planet Earth and you could never leave your living room, that would be a tall task. Now, what that means is we could figure out some basic trends. We would know the overall rough estimates about our planet if you never could leave your living room. But we're certainly never going to know every detail. No matter how long we are afforded to live on this planet, we will certainly not understand it all while we're here. So this chapter begins with this idea of the Big Bang. And of course, the Big Bang is a coined term. And like I've mentioned many times in the past, we use terms to describe things based off an original idea or an original concept of what the thing is. And then later on we find out that's a terrible description. That's not how it works at all. The Big Bang is a great example of that. This idea of a Big Bang being an explosion or some sort of boom is a terrible description ultimately. And the text kind of talks about and if you do some other reading otherwhere on the Big Bang, we realize that we really need to talk about how this is a point of expansion. And the idea is this is all based off of what we can actually measure today. Obviously, no human beings, we weren't around, I was not here 14.5 billion years ago. If we continue to adjust that number, it's probably almost certainly going to get bigger. So how can we possibly know what it started with? Well, we can't know for sure, but what we can know is we can take what we can see right now and make our best guess inference on what we think would happen if what we see happening now is what has always happened. And that's one of our big assumptions, is that what we see is related to what must have happened before. That's one of the big assumptions that we're looking at here. Okay, now, if you look over on 537, thing that I want to point out that I've mentioned once or twice now, but the idea is that the expansion of our universe is expanding, and we have an undeniable amount of evidence to support now the idea the universe is expanding, and in doing so is causing everything to be shifted. The light that we see is red-shifted, giving us an idea of how much it is being expanded. And this information actually was first handled by Edwin Hubble, giving us an idea of how much it is expanding. Here we have one of our first measurements. Actually, this is a little bit out of date because this number has been adjusted. And it says as of 2010, the most accurate measurement for the age of the universe based off of this. I love this simple explanation. This is a great way to think of how we have determined how old our universe is. If we look at the separation distance and we look at how fast they're moving away, all we got to do is figure out then we simply divide them. And so we end up with a number of about 71 million kilometers per second, 71 kilometers per second per megaparsec. Basically, what we turn that into is we say that it must have been expanding for about 13.7 billion years. This number has actually gotten a little bit bigger as of 2010. This number has been adjusted a little bit. I was really thinking that the number was somewhere around 14 billion and some change. But this text has it as 13.7 and some change. It doesn't matter really in the grand scheme of things because we're talking about approximating something that happened tremendously long in the past based off of how fast something is moving now. So we're using a lot of indirect methods to determine this anyways. Now, What are some examples of this? How do we really know what's going on? Well, one of the great experiments that measured this information is talking about measuring cosmic microwave background radiation. That is, looking at the radiation that would have been left over from this moment the universe started. If everything was created at this one instant, then this stuff would have, there would be this leftovers, if you will. It is the cosmic microwave background. When you read through 18.4, which is a section you need to look at, it talks about the idea of this information and how it was measured. Very interesting stuff. That actually, I believe, ended up winning them a Pulitzer Prize. Yeah, they ended up winning the Nobel Prize for their work with the cosmic background radiation. Very, very cool stuff. You also need to look at 18.5, the ideas of isotropy and homogeny, talking about how the universe is the same and different in different directions. You need to understand what's going on in 18.5. And then, I think what we're going to do is we're going to skip most of the way to the end of this chapter. The last thing that I want to talk about is I want to talk about dark energy. And they finally give you some reading on dark energy. So you really need to look at page 555 and look at 1815 and to read what's going on with this concept of dark energy. Dark energy is a fascinatingly cool idea, and I touched on it earlier that must be something driving these objects getting further away. And this is what is a real conundrum with this Big Bang is if everything started in one bang. That's why we don't like the idea of calling it a bang. Then it should all be slowing down. There shouldn't be anything else pushing it. Well, what's pushing it? Something must be pushing our galaxies further apart and is increasing the rate at which it's pushing. It's a fascinatingly cool subject to look at, but dark energy is a very poorly understood concept, as it's only been discovered since the start of the 21st century. But what it boils down to, this is one of my favorite graphics. When it comes down to what do we know? What do we know in the universe? What do we know about the stuff that's out there? Remember, dark energy is a mysterious energy source pushing things apart. We have no idea what it is. Dark matter is the missing energy in galaxies and galaxy clusters. We have no idea what it is. And that makes up almost 95% of our universe. We know very little on the grand scheme of things about how our universe is on the big, what this stuff is. Well, what is it? Right? Well, only about 4.5% of that is normal matter. When we're talking about normal matter is planets, it's people, it's stars, it's galaxies, it's dust, things we can actually see and detect. Everything we can see and detect, we think only makes up less than 5% of the known universe. That is just a fabulously exciting part of understanding astronomy. That there is enormous giant question marks here to be asked about what's going on the grand scale of our universe. The truth is, we don't know. And that is what drives so many people. And it's where it leads me to one of my favorite quotes by Albert Einstein. One of my favorite quotes he said is, I'm not particularly talented, I'm just passionately curious. And it's got to make us all passionately curious as to how does our universe work this way? If we don't know what 95% of it is, what is it? What do we know about how things actually even work? And perhaps there will come a time where we will fundamentally change the way we understand the universe in much the same way that we fundamentally changed the way we understood the universe when we learned about galaxies at the beginning of the 20th century, or when Galileo and Kepler changed our understanding about the geocentric universe in the early 17th century. Perhaps we're on the cusp of needing to totally revolutionize our understanding of astronomy again. So it's a great, great time to be studying astronomy because we have a lot of tools. We have a lot of things to work with, and we have some really big questions about what's going on out there. Dark matter and dark energy are certainly one of the big ones that we will be looking at as time goes forward. Okay, that'll get you going with what you need on Chapter 18. Make sure you read the sections I mentioned. There's a lot of in there we're kind of skipping over, but that'll get you going for the homework on Chapter 18. Good luck.